So welcome for next session on module 4 radiation. And in today's session, let us start with something very important from the practical point of view, like how exactly you will deal with the problem to minimize your calculation related to radiation based problem. In this case, we will discuss a concept which is called as a gray surface approximation. So what exactly is a gray surface approximation? Let us try to understand. So we have already discussed radiation properties, and one of the properties, important property of radiation is your emissivity. Okay, so let us plot a graph for emissivity with respect to your wavelength. Normally for black surface, I will try to use black color just for better understanding. For black surface, sorry, it has to be a straight line. The emissivity of a black surface will be equals to 1, and it will be constant all throughout the wavelength. No matter what is the wavelength, the emissivity of the black surface will be 1. Okay. But for a real surface, first of all, the real surface will have emissivity lesser than 1. Okay, it can have something between 0 and 1, but not greater than 1, and cannot also be negative. So for a real surface, the emissivity curve will look somewhat like this. So what we can clearly see is that the emissivity does not remain same all throughout the wavelength. A different wavelength. A different wavelength, the emissivity of the same surface will be different. This brings a very difficult situation for an engineer who is trying to perform certain practical calculation. Now for every possible wavelength, you cannot find the emissivity value, and then it will become a very cumbersome calculation for one person to execute it. So in that regard, what we do is that we come up with an average value of emissivity for all this wavelength, and we'll assume it to be constant all throughout the wavelength range. So that is called as your gray surface approximation. Okay. Same thing goes with respect to emissive power also. You see, normally this is lambda. Normally a black body will give a curve like this. All right. Now for a real surface, the curve will come what like this. Now in order to have a smoother calculation, we will assume it to be like this. Okay. And this is your gray surface approximation, which because finding an area of this one, a smooth curve, area under a smooth curve is much easier than finding the area under this yellow color curve. All right, so that is why we usually go for uh, this is your gray surface, and this is your real surface. That is why we go for this gray surface approximation. Now with that, let us move on to discuss one more very important concept in radiation, which is called as a view factor. Now here we are talking about radiation exchange between bodies, correct? And view factor gives us an idea like what part of radiation from one body is reaching another body. I will try to illustrate my point with a simple sketch. Let's say we have a point source of radiation, and that point source of radiation is emitting radiation in all possible directions. Okay, and in that scenario we have three surfaces. One surface is like this. Let's call this a surface 1. Another surface is like this, completely perpendicular, so let's call this a surface 2. And another surface is like this. Let's call this as, sorry, like this. Let's call this a surface 3. So as you can see clearly, the surface 1 will receive maximum amount of radiation because it is normal to the incoming radiation, whereas if you see surface 2, it will absorb only a minimum or basically zero amount of radiation because it is the area vector of the surface is parallel to the perpendicular to the area vector of the point source surface. Again, this one will have only a small fraction of radiation reaching it. So view factor basically is, if which is denoted by F, and if I write it at Fij, okay, where I and J are two different surfaces. I is the emitting surface and J is the receiving surface. Then Fij, I can write it as it is the fraction of radiation leaving surface I and striking the surface J directly. All right. Now let us with this particular concept of view factor, let us take some standard cases into consideration. Let us take a flat surface initially. Okay, and radiation is coming out from the flat surface. So if I want to find out view factor of surface 1 with respect to itself, not with respect to any other body, with respect to itself, it will always be 0 for a flat surface. Why? Because as you can see from the diagram, none of this arrow will strike back again this surface. All right, that is why view factor of a flat surface with respect to itself will be 0. This is one of the standard cases. The second standard case that we can consider is that of a concave one. So in this case, again, you can see all the radiation leaving the surface will never going to strike back the same surface. So here also view factor from 1 to 1 will be 0. The third standard case is, sorry, that was a convex one, and this is a concave surface. And here you see a part of the radiation leaving the surface is going to strike back onto the same surface. So 1 to 1 will not be equals to 0 in this particular case. Okay. So these are some of the 3 standard scenarios that we can consider to solve our problem related to view factor, but not necessarily that these 3 concepts are enough. So we have to use something called as the rules of view factor. Sorry. Next thing we are going to study here. So the first rule with respect to, or first relation with respect to view factor is called as the rule of reciprocity. Okay. So suppose 2 surfaces are there. This surface having an area A1. Sorry. And surface having an area A2. And let's say view factor from 1 to 2, F is represented by F1 to 2, and view factor from 2 to 1 is represented by F2 suffix 2 to 1. Then rule of reciprocity says that A1 into F1 to 2 will be equals to A2 into 2 to 1. All right. And we will see the application of this particular relation or with respect to a problem, a simple problem we can take, and we will see in the application of this one. The next rule is called as a rule of summation. Now remember, the rule of summation can only be applied in case of a closed or enclosure rather than closed, in case of an enclosure. All right. So minimum, this rule can be applied only to a minimum of 3 surface. Sorry. Yeah. At least minimum 3 surfaces has to be there, because then only you can form an enclosure. With 2 surfaces, you cannot form an enclosure. And you can apply this rule. Let's say this is surface 1, this is surface 2, and this is surface 3. And you can apply this summation rule for any one of the surface. Now this rule says that, see, whatever radiation is leaving the surface 1, since it's an enclosure, the total radiation will be received or shared by all the surfaces. So I can say that F1 to 1 plus F1 to 2 plus F1 to 3 should be equals to 1. All the radiation that is leaving surface 1 will either strike surface 1 or 2 or 3. And if I take the summation of all of them, that will comprise the total radiation. So since view factor is nothing but a fraction, so summation of all the fractions should lead to a value 1. You can apply it. This is applied for surface 1. You can apply it for surface 2 also. So 2 to 1, 2 to 2, 2 to 3 will be also equals to 1. Similarly, F3 to 1, 3 to 2 plus F3 to 3 will also be coming equals to 1. So And also it does not matter whether how many surfaces are there in the enclosure, 4, 5, 6. You can apply it for n number of surfaces, but only thing is that it has to be an enclosure. It should not be open on any side. Next rule is called as your rule of summation. Yeah, sorry, summation rule we have already done. Superposition. So in rule of superposition, let's say we have two surface. This is surface 1 and this is one more surface. What I can do is that I can split this surface into two different surfaces, 2 and 3. All right. And we will consider them separately. First, we will consider, sorry. First, we will consider 1 and 2. And then we will consider 1 and 3. Okay. Why we are doing this? Because under certain condition, the orientation of the two body may be in such a way that we cannot, if I consider this as one single surface, I will not be able to solve the problem. In that case, we will split this surface into two parts such that the orientation of the body changes. I mean, like, respective surface changes a little bit, and then we can use the principle of superposition, rule of superposition, to do it. So what I can write is that in this case, F1 to combine 2 and 3 is equals to F1 to 2 plus F1 to 3. Remember, you cannot use it the other way around. Okay. F3 to 1 comma 2 is not equals to F3 to 1 plus F3 to 2. Why? Because these two are one particular surface which we have split it into two. It was not the original surface. So that is why you cannot take any one of the splitted surface and apply the the same rule. All right. So it always has to be with respect to from the surface which has not been splitted to the surface which has been splitted, not the other way around. Okay. The next rule, this was the third rule. The next rule that we are going to discuss is your rule of symmetry. I will take it in the next way. All right. So what does rule of symmetry say? So suppose you have three surfaces. Okay. This is surface 1, this is surface 2, and this is surface 3. As you can see, surface 2 and 3 are symmetrical about surface 1. So view factor 1 to 2 will be equals to view factor 1 to 3. What will be the value we don't know, but they has to be same. If they are and the two surfaces are two or more than two surfaces are symmetrical about one other surface. Okay. So these are the 4 rules that we need to apply to solve the view factor problems. Let us see a few of them, few simple problems. So let's say we start with an enclosure, a hemispherical enclosure, let's say, and this inclined line indicates that these surfaces are non-radiative. Only radiation exchange on the other side. This side will not act as any or will not participate in any kind of radiation exchange. So let's say this is your surface 1 and this is your surface 2. And this is a hemispherical dome. And let's say it has an area A2 and this has an area A1 and the radius of this hemispherical dome is R. So the first thing that we can notice is that suppose I want to find all the view factors associated with this particular situation. So all the possible view factors will be view factor 1 to 1, view factor 1 to 2, view factor 2 to 1, and view factor 2 to 2. These are all possible view factors that you have to find. All right. Now the first thing that we are going to do, let us find the area. So A1, since it will appear as a circle, it will be pi r square. And since it's a hemisphere, the surface area 2 is a hemisphere, and area of a surface area of a sphere is 4 pi r square. So for a hemisphere, it will be 2 pi r square. Okay. Now the first thing from the standard cases, we know that if it is a flat surface, then f1 to 1 should be equals to 0. All right. And then we apply the summation rule. Since it's an enclosure, we can apply the summation rule. And I can say that f1 to 1 plus f1 to 2 should be equals to 1. And since this is 0, f1 to 2 is equals to 1. Which also makes sense, since it's a flat surface, all the radiation coming out will be received by the surface 2. Now, if we apply reciprocity rule, I can see that A1 into F1 to 2 should be equals to A2 into F2 to 1. A1 is pi r square and F1 to 2 we have already just found out it is 1. A2 is 2 pi r square and F2 to 1 is unknown to us. So pi r square will cancel and F2 to 1 will become 1 by 2, which is 0.5. That means 50% of the radiation leaving surface 2 will be received by surface 1. Okay. Now I need just last we need to find F2 to 2. So we are again going to use summation rule on surface 2. F2 to 1 plus F2 to 2 will be equals to 1. And this we have already found out to be 0.5. F2 to 1. So we factor from 2 to 2 will also be coming as 0.5. That means 50% of the radiation leaving surface 2 will come back to surface 2 again. Okay, so this is how we can use the concept of view factor and the rules of view factor to solve the problems. Now the last topic in radiation is called as your radiation shield. Now sometimes what happens is that between two radiating surface, I want to reduce the amount of radiation. leaving from one surface and reaching another surface. In that situation, what I will do, I will try to reduce the radiation by applying an additional layer between the two, and that is called as your radiation shielding. Okay, now there are a lot of things that goes into that particular calculation, so those derivations are not there. So suppose I will just take two surfaces, two parallel surfaces, and parallel gray surfaces. I will mention these are not black surfaces, they will be associated with emissivity. Now let's say surface 1 is at a temperature T1 with an emissivity epsilon 1, and surface 2 is at a temperature T2 with an emissivity epsilon 2. Now they will have radiation exchange between them, and that radiation exchange, sorry, radiation 1 to 2. One more thing is radiation 1 to 2 will be equals to 2 to 1, because the temperature of the surface is not changing. Energy in will be equals to energy out, will be given by sigma into T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 divided by A1 into epsilon 1 plus 1 upon A1 F1 to 2 plus 1 minus epsilon 2 A2 epsilon 2. Now here you see, since they are parallel plates, infinitely long parallel plates, A1 will be equals to A2, first thing. So we can just simply take A1 common, A1 equals to A2 is equals to A, we can write it, and we can just take it on the top, sigma A T1 to the power 4 minus T2 to the power 4. Next thing, view factor F1 to 2 will be 1, because all the radiation leaving surface 1 will be taken by surface 2, because they are normal to each other. So view factor 1 to 2 will also be equals to 1. So this middle term will become only 1. And here what we can get, since we have taken A1 common, so this will be 1 if I divide it by epsilon, 1 by epsilon minus 1, epsilon 1 minus 1 plus 1 plus 1 by epsilon 2 minus 1. So plus 1 and minus 1 will cancel, and eventually the expression will become sigma T1 to the power 4 minus T2 to the power 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This is whenever radiation exchange is happening between two parallel plates without any shielding. Okay, as soon as you put a shield between the two, the radiation will tend to the radiation exchange will tend to decrease. Let us see how. Okay, so this is a no shield condition. I will write the expression again. Sigma into A into T1 to the power 4 minus T2 to the power 4 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This is no shield condition. Now let's say I put one shield. So I will take again, this is surface 1, this is surface 2, and there is a shield that has been put in between them. Let's say this is epsilon 1, this is epsilon 2, and the emissivity on this surface, let us represent it by epsilon 1 suffix 3 comma 1. That means emissivity of surface 3 with respect to surface 1, and on this side it's emissivity of surface 3 with respect to surface 2. It can be same. I mean, in a given problem, when they can tell you that the emissivity of the shield is only is equals to 0.3 or something, that means on both the side the emissivity is same. You just have to assume it. So in that case, you can see q1 to 2, the expression will come around a into sigma into t1 to the power 4 minus t2 to the power 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1 plus 1 upon epsilon 3 comma 1 plus 1 upon epsilon 3 comma 2 minus 1. So here you see there is this additional term which is in the denominator, correct? That means if I put a shield, the value of q1 to 2 tends to decrease. Now this is with respect to one shield. If you increase the number of shields, then there will be subsequent more number of terms coming in the denominator, whereas the numerator remains unchanged. In that case, we can say that the number of shield, as we are increasing the number of shield, the amount of radiation that is going from one surface to another surface will tend to decrease. Also, let's say an very unlikely situation, let's say epsilon 1 is equals to epsilon 2 is equals to epsilon 3 comma 1 is equals to epsilon 3 comma 2 is equals to epsilon, let us say. Then in that case, it will come out to be a into sigma into t1 to the power 4 minus t2 to the power 4 divided by, here it will be 2 by epsilon minus 1 plus 2 by epsilon minus 1. So this will come sigma a sigma t1 to the power 4 minus t2 to the power 4, and this if I take both of them common, this will be 2 into, this will be 4 divided by epsilon minus 2. All right. So this is the expression is I mean, it simplifies a lot. So here what we can do, or we can just simply write it like this. This entire expression I can again rewrite it like this. So this will be a into sigma into t1 to the power 4 minus t2 to the power 4 divided by 1 upon epsilon plus 1 upon epsilon minus 1 plus 1 upon epsilon plus 1 upon epsilon minus 1. That this is with respect to one shield. Okay, if two shield is there, then the expression will change. A into sigma t1 to the power 4 minus t2 to the power 4 divided by 1 upon epsilon plus 1 upon epsilon minus 1 plus 1 upon epsilon plus 1 upon epsilon minus 1 plus 1 upon epsilon plus 1 upon epsilon minus 1. This is with respect to two shield. Okay, so here in the denominator what I can write is that a into sigma into t1 to the power 4 minus t2 to the power 4 divided by 2 into 1 upon epsilon plus 1 upon epsilon minus 1. Similarly, here I can write a into sigma into t1 to the power 4 minus t2 to the power 4 divided by 3 into 1 upon epsilon plus 1 upon epsilon minus 1. So the factor changes to 3 when the number of shield is 2. The factor changes to 2 when the number of shield is 1. So if there are n shields, then the expression will be a into q1 to 2 a into t1 to the power 4 minus t2 to the power 4. And since there are n shields, this will be n plus 1. And this will be 1 by epsilon plus 1 by epsilon minus 1. So this is the expression that we will get for a number of shield, provided the emissivity is same in both the cases. So let's conclude here. The other two modules will be covered by Manjay sir. Thank you.